In this video, we're going to show the concept of load leveling and bottlenecks in an emergency department. So what we have here is a simplified model of an emergency department. We've got 9 beds, and we're going to have 2 RNs working all the time except from 5 a.m. to 8 a.m. where we have 1, and an MD going from 2 of them all the time except from 5 to 8. So here I'm going to show you my controls. And what we're going to do is we're going to run this for 1 day, 1D, and I'm going to start it up. And here what we see is a patient comes in to triage, so the patient's the green person, and they take a random amount of time. They're within certain parameters, and then they're going to go to registration, and then they're going to go get a bed. If there's no bed available, then they go to the wait room and wait. All the times have randomness associated with them, so they're all usually within a range of values that they could take. So let's go ahead and speed it up. And we're going to collect statistics too, by the way. We're going to collect statistics on the average bed occupancy, the average length of stay for everyone, the average length of stay for patients who arrived from 5 p.m. to midnight, and how many people had a length of stay of over 5 hours long. So let's go ahead and speed this up a little bit. So if you hear clicking, that's usually me speeding it up or slowing it down or pausing. So now he's going through registration, and now he's having RN assess. The RN comes and assesses. Now the MD assesses, and I'm going to pause it. This person now is having tests done, so they're either getting X-ray or ultrasound, or they might be waiting for a lab test, something like that. This person here is having an assessment done. Not everybody has the test and DI done. It's randomly assigned in this case. So this person's having the MD assessed, they're being treated, and then they're going to leave. One thing this model does not do is we're not modeling boarding. So if they're waiting for a room in the inpatient hospital, they're not shown here. And also we're only showing walk-in patients, we're not showing an ambulance bay. So we had about 5 different activities that are done. And now a real model could easily have 10 times or more than that of different types of activities done, maybe even 20 times more. So we're not trying to capture everything that could happen. We're trying to get a flavor of what happens to show the particular concepts we're interested in for training. So I'm going to go ahead and speed this up. And now you see patients coming and going. The beds still aren't full yet, though. And let's speed it up faster. Okay, now you see the beds are full and there's waiting going on, and we're starting to collect our stats. So let's go ahead and see this on a different view. Here I'm going to show an ED where we're going to run it now for 1 full year. Alright. And we'll restart it from scratch. So we're running for a full year. So this is the same day we already saw. By the way, you can see the time down here in the bottom left corner. So it starts at January 1st at midnight and continues on. And this is going to show the number of patients in the ED over time. So this is always the current time here, and this shows the last 24 hours of what happened. This shows the length of stay. The dark blue line is the length of stay for individual patients. When you see spikes like that, that's somebody that needed a test done, so they had to wait longer. And the green line is showing the average length of stay for everybody in the hospital. Now that's still moving around a lot. That's because we're going through something called a warm-up period. So when the model first starts, there's nobody in it, so the first couple people in, they take no time at all hardly. They go right through all their activities. They don't have to wait for anything. So in a real simulation model, if we were doing a study and analyzing the results of a real hospital, we would discard that warm-up data and only count what's called steady state. In other words, once everything's leveled off. But for our purposes, it doesn't impact us much, so we're just going to go ahead and show it. Now notice as I run this, that this red line, we're getting so many patients in at the peak times that it actually goes off the graph. Okay, we're not even seeing everything. And the length of stay, of course, depends very much on, it lags the number of patients by a little bit, because as there's a peak, it takes some time to clear those people out. So that's why you're seeing them slightly out of phase on these two graphs. Notice by now that the green line, the average length of stay for everyone, is leveled off, and that means that we're probably getting near the beginning of our end of our warm-up period. So let's go ahead and speed it up some more. And we can run it 1,000,000 times fast, which basically means as fast as your computer will go. And we can see the people coming in, going out. And we're definitely starting to see patterns now. So we're up to July already. And 1 year is usually long enough to run a real model unless you're looking for seasonal variations, which we don't have in this particular model. Okay, so we ran it for a full year, and we've got some statistics. So bed occupancy is 7.6 beds filled on average. So during the day and after the peak, they're very full. It's only a little bit during nighttime when some beds clear out, when the patients go down to very low numbers. The average length of stay, 183 minutes, so about 3 hours. Average length of stay for people who arrived after 5 o'clock until midnight, 281. So those folks have to wait a lot longer. And the number of people that stayed greater than 5 hours is 5,808. So not a good experience for them. They're not feeling well, and then they're in the hospital waiting mostly for more than 5 hours before they get out. The total number of patients that entered is 48,180. And let's see what we could do about this peak, though, because that seems to be causing us a problem. That's the people who are waiting a lot longer, and it's probably causing most of these greater than 300-minute stays. So let's go and see if there's anything we can do about that peak. And let's look at the people who are arriving in the hospital. What we have here is that this line here is red and green, or red and blue, I mean. The blue is just underneath the red. And that's the people we're doing. And the one we just saw was the blue line. So the blue line is the peak that we're hitting and then going down. Now what I did is I researched arrivals on the internet, and I found some good examples of real arrivals at real hospitals. And then I tweaked them a little bit to match our model. So it's not exactly the same as I found, but it's based on some statistics I found online. So basically, we've got this big peak, and that's causing a problem. What could happen if we can level out that peak and make it do what the red line shows? For example, there's a local hospital to me that they have a wait-at-home program where you go on the internet and you can reserve a place online and come in later when it's your turn. And then that way it avoids congestion at the hospital, and you have to wait less while you're there. But let's not get quite that fancy. Let's just say we've got some kind of program, though, where we let people know if you're coming in at 5, 6, and 7, try to come in later if you can. Okay, obviously some people aren't going to hear the news and they're not going to know, and there's other people that feel that they do need to come in right away, and that's fine. But there's some people that they know they can wait a few hours if it's going to make their overall experience more pleasant. So let's say we can reduce this peak, and just for these 3 hours, and have them delay a few hours and come in later in the evening. So if we're able to do that, what will happen? So let's make the simulation model do that. And what I'm going to do is I'm going to go to this one here that says select arrival pattern here. I'm going to right click. I'm going to say input editor. And I'm going to take this one that says arrival pattern, which is the original pattern, and I'm going to change this value to a 2. And what that's going to do is that means we're going to use the leveled or the red line that we had. And what I'm going to do is I have to hit enter or click on a different line to make sure it registers. And then the simulation will use that new value. So let's go ahead and run the same model as we did before. And we'll slow it down a little bit to start. And here it comes, and we're getting the same total number of arrivals. The only difference is the times they come in are going to be a little bit different. So you see here we're starting our warm-up period on day 1. We're going to speed it up a little bit. Now we're going at a pretty good rate. And we're starting to gradually leave the warm-up period and enter the steady state. There's not always a clear defining line exactly when that happens. There's lots of statistical tests you can do to say exactly when that happens, but it normally is a kind of a gradual thing. But we're probably in the steady state range now. And I'm going to speed it up. Notice that we're not going off the graph anymore. The other one, the patients in ED was so high during the peaks that it wasn't even showing on the graph. Now we're going near the top, but we're not going over it. So we're collecting new statistics on everything that's going on. We're up to October. And here we go. We've done one full year. And let's look at the statistics on that one. So recall that here's the pattern that we're following, where this is the number of patient arrivals per hour. And for example, from hour zeros from 0 to 1 o'clock, we had 3 arrivals. From 1 to 2, we had 2, etc. 132 a day. So let's see the impact that that had on the results. So scenario 1 was our original arrivals, and scenario 2 was the one with the leveled arrivals. Okay, the red line. Bed occupancy stayed the same on average. Average length of stay, and this is for everybody in the hospital, not just those we leveled, went down. So it looks like it went from 183 to about 170. So it went down 92.6%, or it looks like a 7.4% improvement. That's pretty good. We only changed people for 3 hours, but it improved everybody's length of stay by 7.3%. If we look at people who arrived from 5 to midnight, they went down to 244 minutes. So they are at 86.7% of what they used to be, or looks like a 13.3% improvement. So they're much happier. But here's where we got a real gain. For people who came in and stayed more than 5 hours, we had over 5,800 people did that. Now we've only got 861. So if you define having a truly miserable experience waiting more than 5 hours at the ED, and if you could say that you knock that number down by 85%, that's pretty good. So the people who were really suffering that came in at the busy time, because we told them, hey, come in later, had a lot less waiting. They'd rather wait at home for a few hours if they're able to, and then come in a bit. But they may not have known that that was the best time to come in. So we've got that. Definitely an improvement. Let's go back to this graph now and think what else we can do. The low leveling helped. It definitely was worthwhile. What else could we do? What if we had more beds? If we had more beds, would that help? Because the beds are filled completely during the day. It hits 100% filled. And during the peak hours. Only at nighttime for a little bit does it clear out. So let's see if we could look at that. There's one here that says change number of beds here. If I right click on that and say input editor, I'll see that it lets me open and close beds, but it doesn't let me add any beds. So well, let's go ahead and try closing one, see what happens. So if I make a 0 here, that closes it. So 0 will close bed 9. Okay, and I remember to enter or click on a different line. It registered. So now when I run the model, nobody will go to bed 9 because bed 9 is closed. And let's go see how this works for a year. Before I run it, you can stop the video and predict what you think will happen. Okay, so if you're still watching, I'm going to assume that you've decided what you think will happen. And let's go ahead and run it now. So the patients are going to come in, and I'm going to go speed it up. Okay, we're going through our warm-up period. Looks like we're in steady state pretty soon. And we're collecting statistics. So we'll go ahead and let this run at full speed. If you have a faster computer, this runs faster. A million doesn't mean it's going a million times. It means it's pretty much doing what your computer can do. And there we've got a full year now. So let's go ahead and look at the statistics. We've got it recorded down here. We had the same number of patients arrive. Let's go ahead and see a summary of them. And if I look at the tab here, it says results all. Here I've got scenario 3 where we did the level load, but we've only got 8 beds instead of 9. And what happened is occupancy went down. You'd expect that. And then average length of stay went down very slightly. And the average length of stay for people who arrive after 5 p.m. also went down very slightly. And the number whose length of stay was greater than 5 hours had a good drop. It went down, it's like over 150. So a pretty good drop there. So that tells us that in this particular case, and it won't always be the case, but for this particular model, removing that bed actually helped. And the reason is because instead of patients waiting in a chair, all that bed did was have one more patient wait in a bed. If you look, it says waiting, 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 waiting. So these folks are all waiting for an MD or an RN. And in this case, we see that there's only one RN, and there's 2 on shift. So we know that they're not waiting for the RN, they're waiting for an MD. And the bottleneck in this model is the MDs. They're busy almost all the time. They have only a few minutes in the middle of the night when they're not working. So near 100% utilization of the MDs. So if you fill up an extra bed, what happens is an MD goes and starts them, and now they got more people to work on, and they got more work in process that's not being finished. Whereas with the one less bed, they actually were able to get the current patients done and out of there, reducing the length of stay. While at the same time, because they were still always busy and had plenty to do, they were never idle. So we never had our bottleneck idle, but instead focusing on getting a set number of patients out instead of starting a whole bunch and not getting them out as quickly. So closing that bed actually helped. Now, if that helps or not depends a lot on if that's the bottleneck or not, where your bottlenecks are. You could try changing the numbers and seeing if closing more beds would help. But if you go too far, then the beds start to be the bottleneck, and you'll end up making your MDs be idle, which is not the thing you want to do either. So in this case, we see that realizing that bottleneck is the MD is a key takeaway from this exercise. If we look, what else could we do? Well, what we might want to do is we leveled the load as much as we can, but we might want to match it a little bit better too. And maybe we could have a little bit more off time of the MD at night and move them during the peak time a little bit. Maybe have 3 of them working at night. That might not be possible though. Maybe we're in a small town, we're having trouble getting 3 MDs at nighttime to come in and work. So that could be it. Or we could hire new people, maybe hire a physician's assistant. But just throwing money and bodies at a problem usually is not cost effective, and also it's usually there's a better way to solve things first. That should normally be a last way to do it. So are there process changes we can do? If we could take even 15 seconds off of an MD task in a model that's running this close to the extreme edge, you'll start to see a difference. So can you make any change that won't impact the patient care that could take time off of the time that they have to spend? Is there a technology we could add? Or could we do other staff adjustments? So I'll let you discuss what might be reasonable in a ED like this, and I hope that you enjoyed watching the simulation model and learning about load leveling and bottlenecks. Thank you.